it consider a single view RGB image and LiDAR bird's eye view representation as input. And they use several transformer models for the fusion of intermediate feature map between both models. And the fusion is applied at multiple resolutions throughout the feature structure, resulting in the 512 dimension feature vector output. So this 512 dimension feature vector consists of a compact representation of the environment that from the RGB image and the LiDAR bird's eye view image. And as Haopeng and Xiaoliu have also introduced some background of the transformer. And here we also use it on this task.
I have a question in the previous slide. Can you go there once?
Okay, go ahead.
Yeah. So here now the RGB image and LiDAR information after going through the multiple layers, it's being given to ResNet 34 and ResNet 18, right?
Yeah.
So what are these two models, ResNet 18 and ResNet 34? Are they like because LiDAR information and RGB information is separate? They're not similar kind of information. So do you know what they do in this?
Well, it just use some convolutional feature extraction and putting to the image and the LiDAR bird's eye view data representation. The image is represented by the pixel, and the LiDAR bird's eye view also can also convert it as the pixel. Since that is also why we have to convert the row point cloud to the LiDAR bird's eye view, or rather why we cannot just use the row point cloud. This is to make it to the LiDAR bird's eye view, it is to want to make it more compatible with the RGB image. So that bird's eye view, you can just consider bird's eye view as a kind of image. Yeah, and they have pixel. And since in here we have both, they have both converted into 256 by 256 pixel. Yeah, it's just use this in this ResNet framework. Yeah, they are some kind of feature vectors you can imagine. Yeah.
Okay, thank you.
Yeah, you're welcome. Yeah, and for the transformer, basically it is composed of an encoder and a decoder. And before the encoder, there's you can add a positional encoding, and for the encoding and the decoder part, the most part is a multi-head attention and a scaled dot product attention. The input are as a V, K, and Q. And different from the Haopeng's paper, they use the transformer to do our NLP problem like the code generation. But here we use the transformer to do the image like object detection problem. So the input here is some intermediate girder structure feature map. Like in this figure, like the Q are represented as the girder structure feature map, as they use it as the input of the transformer. And the convolutional feature extractor of the image showed on these figures, and the LiDAR bird's eye view input encode different aspects of the sense at different layers. And it views these features at multiple scales throughout the encoder. So they use multiple features extractors. And let's have a closer look about the transformer itself. It says that let the intermediate girth structure feature map of a single modality be a 3D tensor, h height by width by channel. And for S, different modality, these features should be also multiplied by the S. And here S equals 2, since there are camera and LiDAR. And before this input, it actually add a learnable position encoding. And here we show learnable position encoding, and in this dimension, so that the network can infer spatial dependence between different token and trend type. And also it provides a current velocity as input. All these are the input in the transformer. So actually, for the simplicity, they have omit the positional embedding and the velocity embedding input in this figure for the clarity. Yes, and for each intermediate tensor is fed as an input to the transformer, which produce an output of the same dimension. And this fusion is applied multiple times throughout the ResNet. And another trick is that since processing feature map at high spatial resolution is computationally expensive, so it first downsample higher resolution feature maps from the early encoder blocks using average pooling to a fixed resolution X, H, and W to 8. So here, like even if the block is 64 by 64, here the input is actually 8, and the output is actually 8. Passing it as an input, and then they upsample the output to the original resolution. So here, which restore to the 64. And here also 32 to 8 and 8, and here 32, and so on. So it obtained, finally it obtained a feature map of a dimension 8 by 8 by 512 feature from the feature extractor of each modality for the input of the resolution. So this feature map will reduce to the dimension of 1 by 1 by 512 by average pooling, and flatten to the 512 dimension feature vector. And then goes to the waypoint prediction network part. It passes the 512 dimension feature vector through a multi-layer perception to reduce to the 46, and then pass it to GRU. The GRU is also the model proposed in this paper. They just use it to do the feature waypoint prediction. And for the controller, they use 2 PID controller for the later and longitudinal control to obtain the steer, throttle, and the brake value from the predicted waypoint. And the PID controller are also a model proposed in this paper. They also use it to do that. So actually, in this framework, you can see that they just the key motivation is a key contribution is the transfuser. They just for the later waypoint prediction network, they just use others works and to make this framework in a who to doing a who autonomous driving task. Actually, they can just use the transfuser to do the object detection part and navigation task. And for the loss function, it just use the L1 loss between the predicted waypoint and the ground truth waypoint from the expert. And now I will introduce the experiment and result conducted by them. We have a quick review. The task is point-to-point navigation. The goal is to complete a given road while safely reaching the other dynamic agent. The roads are defined by sequence of sparse locations in the GPS, and they use a color predefined scenario. You can click by this link to see the further details. And in this links, they have predefined some adversarial situation like obstacle avoidance, unprotected turning at intersection, vehicle running red light, and pedestrian emerging from occulted region to cross the road at random locations. So the agent need to complete the road within a specific time limit while following traffic regulation and copy with high density of dynamic agent. And for the data set, they use a color simulator. And for the metrics, they use the road completion and driving scores and infraction count. The driving scores is a road completion weight by infraction multiplier that account for the collision with like other pedestrian vehicle, other things. So they compare the driving performance in their approach against several baseline, and they conduct an infraction analysis to study different failure cases. For the implementation details, they let the multi-layer header equals 8, and they use the ResNet 34, and it is pre-trained on the image lab to extract the RGB image, and they use ResNet is 80 to extract the light upon bird eye view feature. But the paper do not mention why they choose that. Maybe they just try and find they have the best suit on this task. And they use one transformer per resolution and 4 attention heads for each transformer. And for the baseline, they use this, the CILRS and LBC and AIM are 3 currently published model. And the later fusion is a model constructed by their own, and the geometric fusion is another like this. And from the ABC, they are just the image-based method. They use them as baselines to show the necessity of the multimodal fusion design. And the D do not add transformer or fusion strategy, while the E use the fusion strategy, but not use the transformer. They use it to show the state-of-art performance of using a transformer model. So for the performance result, they conduct a lot of experiments on the color Town 5, and they both use the scenario with scenario and non-scenario. And you can see that CILRS perform poorly on all evaluation settings. This is the paper says that this is not surprising since it is the data distribution in it is imbalanced. And for the LBC, you can see its performance drop dramatically when evaluated on the long route. The author says that this is due to the frequent red light infractions and collision with vehicles, resulting in large penalties on the driving scores. And this result shows that the first two methods are unable to handle the complexities in the urban driving. Oh, and another thing that they find AIM is a strong baseline. It significantly output other two methods on all evaluation setting. It shows a good performance on the autoregressy. The authors say that it may, due to that, they use the autoregressy GNU-based waypoint prediction network. Yeah, so it shows that this network is good in this task. And the last three experiments can be regarded as a comparing group. You can see that the fusion transformer method, TF method, has a relatively better performance when there are some scenarios. If there are no adversarial scenarios, the performance cannot be the best. But as there are some unexpected scenarios, the performance from other methods can drop more dramatically than this method. Yeah, so you can actually have a feeling that using this method, using their TF method, is more cautious. Yeah, and more focus on dynamic agent and traffic lines. You see that, for example, you see the GF or the LF, even if the RC, their row completion score is higher, but their driving score is not so high. And remember that driving score is a row completion weighted by an infraction multiplier that account for some collisions. So you can have a feeling that under the LF and GF method, they just focus primarily on navigation to their goal at all costs, while they may ignore obstacles which lead to several fractions. So it shows. So in this three method comparison, it can show that using their method is more cautious, and it also indicates that attention is effective in incorporating the global contextual sensory. And the paper shows that say that they have a limitation. That's to detect the real light is very challenging. Is that all fusion methods struggle with real light violation? As they for the future work, they may want to use some semantic supervision method or to improve this issue. And now I will conduct some analysis. I will show their analysis about their experiment. Firstly, they do some visualization about the attention map of the transceiver to show what the model actually learned. They use end-to-end method compared to the previous the pipeline method. Like you can see, the pipeline method, you cannot, the interpretability may not be good. So they want to show the feature, visualize the attention map to show what the model actually learned. And you can see from the picture, from the yellow query token, they can show the green. They have shown the green screen that highlights the presence of the top 5 attendant token. And you can see that the green, in every picture, the green square is similar, equals to the red square, which is the ground truth car. So that it shows the transceiver does learn something, and shows the accuracy on the visualization part. Yeah. And then they do some present some ablation studies on a number of scales, attention layers, shared or separate transformers, and positional embedding things to show why their default configuration should be the best choice. They have the four conclusions. The first is that multi-scale fusion is essential, since a different convolutional level can learn different type of feature regarding their input. And then they show multi-transformer is necessary, since each transformer had to focus on fusing different types of feature at each resolutions. And it also it also shows that multiple attention layers are required, since it leads to cautious driving agent. The multiple attention layer is here. You can see the L. Even if you can see when the multiple attention layer equals to 1, the row completion score is the best, but its driving score is not as the best. So this is also the similar situation about previous these two methods, that they have high RC but relatively not so high DS. So this shows the least attention layer cannot be not so much cautious, and the 8 attention layer can have a more cautious, can lead to cautious driving. And they also show that the positional embedding is useful, since the modeling spatial dependence between dynamic agent is crucial for self-driving. Yeah, so here comes their conclusions. In this paper, it demonstrates that the limitation learning policy based on existing sensor fusion approach are unable to handle adverse scenarios in urban driving. For example, the unprotected turning at intersections or pedestrians emerging from occluded regions. And it proposed a novel multimodal fusion transformer named the transfuser to incorporate the global context of the 3D sense into the feature structure layer of different modalities. And then finally, it experimentally validated their approach in complex urban setting involving adverse scenarios in color and some state-of-art performance. So at the end, at the last, I'll put the screenshot from this paper to facilitate our discussion about the paper, as well as the multimodal fusion strategy in autonomous vehicle, this field. This table basically lists some challenges and open questions in this field. And for example, for the multimodal data preparation, for the fusion methodologies, I hope you guys can have some inspirations from it. And also that's all my presentation today. Thanks for your time, and I hope you guys can learn something. So thank you. And now, do you have any questions?
Okay, I think the talk is good. And during the talk, my computer crashes, so probably the recording is incomplete. Anyway, we can move to the discussion and the questions. Any questions from the audience?
Hi, I have a question.
Okay. Yeah, go ahead.
It's like about the evaluation part. It seems like they are only trying to evaluate if the multiple transformer, like in different level, is like useful or not. But do you think using a transformer is really necessary? Because it seems like they are only use it for self-attention. Do they do anything like, because I didn't check the appendix, so do they do anything like trying a smaller self-attention model only to do what they wanted? Just because the FPS right now is pretty low, so probably not real time for without further improvement. So probably using a smaller model, smaller self-attention fusion model can improve that. So what do you think on this?
Yeah, I think it might be one possible research directions. Since this paper is very new, they just before the paper, no one have such attempt to do the multimodal fusion on the specific autonomous vehicle, autonomous driving field. They are the first paper to use the transformer and use the multi-layer fusion on it. And so there's no previous comparison, previous work on it. I think maybe, yeah, you are right. Maybe they can use the transformer with at least layers, yeah, to show if they still have such a good state of art performance. But after all, they just use their default setting, and they just conduct the experiment and have such a relatively good performance. So yeah, that's their work. Yeah, and your idea, I think it's also good. It's also can be one possible future direction.
Yeah, thank you. Yeah, because I think some of the attention related evaluation somehow is a bit questionable, like what you just mentioned, like using multiple layers somehow gets a worse result. So I guess I didn't actually quite get how attention is like take part in the whole fusion fusion methods.
Yeah, actually, there's a feeling that I think the multi-layer part can increase the driving cautiously, can increase the driving safety. As I mentioned, there in their experiment, their ultimate performance may not be the best on the road completion, but their relative driving score can be, and sometimes can be the better, and especially there are some adversarial scenarios on it. So by this ablation studies about the attention layers, it also shows that using multiple attention layers can contribute to the overall driving scores, although it may not contribute to the road completion, but the overall performance can be more like in a direction of be more cautiously, be more safety. Yeah, it's like that. It's like that feeling. Yeah.
Yeah, thank you.
You're welcome.
Yeah, for this question, I think the point is good. I mean, the paper probably lacks the motivation to use transformer for the fusion, right? All the experiments lack the sufficient experiments to compare the fusion components with different choices. Then if they can add more motivation description, also add more experiments to the paper, then probably it can make the paper more convincing to use transformer as the fusion components. I think it's a very good point. Yeah.
Yeah. I think.
Yeah. Any more questions from the audience?
And like about the same point,
Okay.
like quick addition about the same point. I think like when I look at the big table with all the results.
You mean this table? Okay.
Yeah, and this table. I mean, I think like late fusion actually with very simple addition of concatenation of all those features performs quite good actually when compared to I think 5 state-of-the-art attention transformers, rather than I mean we have a significant loss in the computation time, also training time, also we have advantages in the non-adversarial scenarios, because in the non-adversarial scenarios it performs significantly worse I guess than the late fusion model. So I'm exactly not exactly sure if I would choose the transformer version. if I wanted to choose like one of these two, because I mean, it looks like concatenation, just like simple concatenation, performs actually reasonably well.
Yeah. It's I think it's one trick. Yeah, in its original paper, they just show very short result with only scenarios, and in their supplementary material, they show that with non scenario, and this snapshot is from that supplementary result. And also, what you mentioned is that long table also shows some comparative good performance on the LF and GF. So yeah, their method actually is not as strong as we may imagine, and as not so strong. Yeah, but there's exists some trade-off, like the memory, the accuracy, speed trade-off, as I mentioned before, like I see, like the speed accuracy trade-off or memory robustness trade-off. Yeah, also the baseline method they compared is more easier. Yeah, the model is not so complex. This is also one point about one weak point. Yeah, one possible weak point of this paper. I think so.
Yeah, thanks.
I also had a question. So in the start, they mentioned that they are combining the feed from a camera and a LiDAR, but that model performs significantly worse than the benchmarks. Then they put two cameras on the two front side of the car at 45 degrees, and then they perform their experiment, right? So do you think they don't provide a reason of why they exactly chose only two cameras in those two particular positions? So do you think there is a particular reason of choosing those only two cameras in those two particular positions? Because it seems like the more you increase the camera, the more they'll be able to accurately avoid the adversaries, like placing a camera on a side as well.
Yeah. The reason why they choose the RGB image and bird eye view, I think it's they just say they may be more be compatible with each other, and I think they do not show why they do not choose other like input data representation. They just use the since actually there's in this object detection in autonomous vehicle part, most of the researchers use the two image representation as an input, like the camera and the LiDAR. I think that's it. Maybe that's also the author did not mention why they use it.
This probably also depends on how they connect the data. Right? They connect data by using the Carla, right? I mean, it's an open source app for connecting data. Right? I mean, I didn't check the Carla actually. I'm not sure if the Carla can allow us to connect the data. I mean, from side view. I mean, nearby. I mean, on each side of the cars to have more image for the car. I mean, during driving or not. I'm not sure. So probably it will be easy for them to connect the data by Carla by capturing the front view of the images, also probably the LiDAR, this kind of data as well. I didn't check this yet, but if you prefer to use more images, I think there's way more data set where we have more images, right, for the vehicles.
Yeah, by the way, I can see there's this is why the advantage of using the virtual plan for the Carla rather than some physical testing cars. Using the Carla, you can use your define the user mode and define the scenarios by your own, and you can collect the raw data. Although maybe not in reality, but the amount is huge. This is one of the advantages of the using Carla.
It's easier to control, right, for the car.
Yeah.
Is there a study which defines the placement of like cameras? I understand the placement of the LiDAR on the bird's eye view, but is there a study which defines the optimal placement of the cameras and maybe the number of cameras that you should put to, optimize your results?
So for car now, can we add more cameras or not?
You mean, sorry, I not understand your question. So do you mean you want to add more image, like image representations about?
Yeah, I understand that adding more images will certainly lead to a better results, but we have to also balance between the computation time and the number of input features that we can process. But I was asking if there is a study which defines the optimal camera placement. Maybe so say if you are working under a constraint, let's say you can only attach 2 cameras. So is there a like a study which defines where those 2 cameras should be placed, the optimal position, something like that?
Yeah,
because that is also a variable, right?
Yeah, that's also one. I think it's one direction. For example, if you see the Waymo open data set, their car are equipped with 5 camera, with 5 different direction, and
exactly.
Yeah, and they just use a camera or a front view camera. Yeah, they can use they can use the camera with the different views, to do the multi-fusion model. And you see here, it's just use the RGB camera, not RGBD. So the deep information are solely provided by the LiDAR bird eye view. So this is also, I think, is a possible point to improve, since it is a 3D object detection problem. But the deep information are just from one kind of the modalities. So it says it has some fusion, but it can have some much more operations on its sensor fusion and input data. Yeah, I think.
Yeah, for this question, probably, I mean, in the real world, when we do the self-driving, probably the computational power is not a concern. And for Tesla has 11 cameras, actually. I mean, in one car, it can capture the surrounding like 360 degree, all the views at the same time, actually. So I think computational power is not a concern for the self-driving. Normally, they need to buy very expensive equipment for the self-driving car because it's very important for safety, to ensure the safety for the drivers, right? So I think the computational power should be okay. I mean, for most of the cars nowadays, they have a large number of cameras. Yeah. So, but anyway, I think your point is very good. If we have a sufficient, if we have a limited computational power, then how can we, I mean, place the cameras to decide the angle to capture the views, right? I mean, then we need to define this problem, I mean, as well. So it's a very good point.
Yeah.
Yeah.
Yep.
Yeah.
Thank you. Thank you very much.
Yeah. Any more questions?
I have a quick question.
Okay.
As you said, the transducer incorporates global contextual reasoning by combining both image data and the LiDAR data. But the input data of the transducer from LiDAR it's a bird eye view. That's 2D data. But the original data of LiDAR is the point cloud data, right? That's a 3D data.
Yeah.
So you convert 3D data to 2D data and feed this data into the model. But mapping 3D data into 2D plane is always lose some variance of information. So why didn't we just feed the original data of LiDAR, like point cloud, the 3D data into the model, rather than convert it to the BEV data structure and feed it into the model?
Well, I think it is for the reason that the LiDAR bird eye view is more compatible with the RGB image. You know, the point cloud is a kind of sparse data representation, and it contains the information from the 360-degree panoramic field. The image data representation, however, it's much denser. So if you just beautifully combine these two definitely different data representations, they may not contribute to a very good result. So they first project the point cloud to the bird eye view and have to make the LiDAR part data input have a denser information to make it more compatible to the image input. And then the fusion transducer model can have a better fusing performance. I think it's this due to this reason.
Okay, that makes sense.
Yeah.
Thank you.
Does this also answer the question asked earlier about the camera placement? Because you want to fuse the RGB image and the LiDAR input. That's why you have a camera angle of 45. You have two camera angles of 45 degrees, so that you want to fuse it with the camera input that's pointing forwards. Can it also be the answer to the question asked previously by some? Because you want to fuse the two inputs. You want the fusion of two inputs. You want the fusion of RGB image and the LiDAR sensor. That's why you have cameras angled at 45 degrees to each other, so that they only capture the scenario at the front of the car.
Yeah, this is I think this is also they just focusing on the front view. You see the RGB image and even the LiDAR bird eye view, they just project towards the front. Actually, in some more researching work, they have more data from other side, like the left, right, front, the left, front, left, front, left, and these things. Yeah, and also maybe their LiDAR can have more field of view. Yeah, so this is, but their main contribution is that on the front view, really only on the front view they use the model, and they can deliver such performance. So this is one of the choosing trick, I think. They just choose to do the research and the performance comparison on the front camera view, this track, not to compete with other track, with other models. And maybe, and on this track, they get a good, very good performance. And this is why.
I also had a question regarding the positional embeddings. So
okay.
What significance would they have in this semantic setup? I mean, like, what would they mean here? Because we are not taking the input directly. We are taking the input when it comes out of a convolutional network. Not here. I mean, in the pipeline.
In the paper, it just shows that the positional embedding contributes to the infer spatial dependence between different token and trend type. Yeah, it just have such introduced, and they have their code. You may, maybe we have to see their code to see what actually their learnable positional encoding is represented in their real implementation version. Yeah, the performance is to infer spatial dependence between different tokens, they say.
All right, thanks.
Yeah.
I have a question.
Okay, go ahead.
Yeah. Do you think this framework or this design is overkill to for this? I mean, camera plus lidar and to detect or just track everything on the traffic? Because I saw some paper 2 or 3 years ago, maybe they just use RGB and with a depth camera or just lidar, and then they use a very simple neural network with fewer layer perceptions, and that's good, already good enough. Can detect people or detect other vehicles, even can have a description on the vehicle, how big it is, and also they can check the green light or something. But for here, it's 2022, and again, it come out. Do you think this model is overkill because the problem is solved many years ago?
Yeah, yeah, that's also an old philosophy. Yeah, for example, in the deep learning field, the model, yeah, also many people argue that there are large the currently model are so complex, and they might wonder that prefer some classical and simpler model. But I think, yeah, you are some point right at some point right. But I think the fusion should be a future direction. The model itself may be least, maybe it may not be necessary to be so complex, but the multimodal fusion itself, it should be one future direction, since each sensor has a different their nature. Positive and the only when the fusion can get the global contextual information about the world. Each sensor, if you just use one kind of sensor, like you only use camera based or the lidar based, they have some this track has been very mature in the last few years, and now their performance seems very high enough. But and also, yeah, the Tesla, they say that they want to have to manufacture a car with only camera based the system. But I think the multi-sensor fusion should be a future direction. And other, except Tesla, yeah, all other company are just also do this direction, and they want to extract some the advantage along each model to get the best video.
Yeah, I agree with you. Tesla is not always be right.
Yeah.
Okay. Yeah. Thank you.
Yeah. You're
also like we need to acknowledge that this task is significantly harder than like some of the like supervised tasks, such as like pedestrian recognition or just like 3D bounding box detection or things like that. Because I mean, first the task is like very complex, so you not only need to just like understand the surroundings and the like context, local and global context, but you also need to make decisions about it. And the worst thing is that we get a very sparse like supervision signal, because we only get the like expert like trajectory of the car, where like it doesn't say, for example, why those decisions are made. It only says the decisions at that frame, for example, what the expert decision was, and now you need to understand like everything about, okay, oh, like I need to detect a pedestrian, for example. This is like in the black box of the deep model. Okay, like when if like there are things like pedestrians, I'm not gonna go that way, and things like that. So like it's very complicated. So I think it makes sense that these models are more complicated than just like simple supervised models with like dense supervision, and then also just like one-on-one supervision on like in very simple things like like pedestrian recognition and so forth.
Yeah, I think so. Yeah. Like,
Okay, so any more questions? Okay, so if you have no questions, then probably that's it for today. And this paper is very different from the papers we discussed before, right? You can see this. Normally in university, we prefer to write paper like this, right? It will be easier for us to handle. As to the paper we discussed before, there are many from the industry, right? So again, you can see the paper style is very different. So probably that's it for today. And in the next week, we'll move to the deep learning section. And the paper we plan to discuss on next Monday with Shen Wu and David. They will be discussing the mask autoencoders are scalable vision learners. So for the presenters for next Monday, and you can prepare for your presentation or send slides to the TA before your talk. Okay, so that's it for today. And thank you so much for your attention.
Thank you.
okay. Okay.
Yeah, somehow we probably can have a meeting after the class.
Okay. Yeah. I have no.
Have a great rest of the week, Professor. I'll see you on Monday.
Yeah, see you.
Bye.
Professor, can I ask a question about a potential idea about this paper?
Yeah, sure.
So do you think it would make sense to, for example, for this model, just like further, for example, help the model, just like define some like auxiliary losses, for example, that are just like other like supervision signal. For example, like I think one of the biggest problems with this model is just like model is very long, and then it's very hard, for example, to supervise the feature detectors, because the feature detectors cannot get like useful gradients only with the just like if the decision was wrong, like right or wrong in the very end. But for example, we can just like make some auxiliary losses so that, for example, the feature extractor would predict, for example, pedestrians or just traffic lights or other cars. And then that would help the feature extractor focus on the things that that are just like important in the scene, and then be better at like what it is doing. But also this like auxiliary loss would help the general understanding of the whole model. Do you think that would make sense?
If I understand correctly, you mentioned, I mean, we can maybe build some components to detecting some specific type of objects, I mean, with a model first, right? And then we can fuse them together, right?
Like not exactly like that, just like this model architecture stays as the same, but also we have like some separate outputs from the model that predicts
So it would be for multitasking, right? I mean, besides the task we do the driving, we also generate some other outputs for training the model, right? I mean, for object detection as a task, right?
Yeah, as a like multitask learning, but that would, I think that would also help this task to be better.
Yeah, it really depends, because I mean, different tasks we will have different objective function, right? If we do the optimization, I mean, for one task, and sometimes it can, I mean, be beneficial to each other. I mean, it can provide complementary information for training the model, right? Sometimes, but sometimes it can also provide contradictory, I mean, supervision information in the training as well. It really depends, because for this model, they are training to, I mean, to generate the driving behavior, right? I mean, even though they say it is imitation learning, but actually it is supervised learning, right? But if we add some more tasks, it depends. I mean, we need to try then decide to see if this kind of add multitasking into the framework training will work or not. I think the idea is good, but we probably need to try it, right?
All right, thank you.
Yeah, we can try this. I mean, if you are interested, yeah.
Okay. Yeah, I think we can maybe work a little on this idea to see if that kind of works, and then if we can find a good proposal about it. Thank you so much.
Yeah. Sure. Oh, hi, Ming. Do you have any questions? Okay, so I think everyone leaves. Then let's
Okay,
have
yeah.
a meeting. Let me
Okay, yeah.
let me end the recording first.
Yeah.